Now, if I draw the waveform after the diode and capacitor stage, which forms a simple diode detector, let us see how this waveform will look like. It will extract nothing but the negative envelope as we have just now discussed, but obviously this negative envelope will be extracted with a lot of high frequency components. This high frequency components or high frequency ripples will be there because if you remember, the capacitor has to discharge between the two cycles. So between the peaks of the two cycles, capacitor will discharge and then again charge to the peak of the next cycle and so on. So extracting just the envelope will not give us my original modulating signal. We have to now somehow remove this high frequency ripples also, which represents charging and discharging of the capacitor. So to remove the high frequency ripples and allow low frequency signal to go ahead in the circuit, we will use the low pass filter. So this R1 and C1 combination forms the low pass filter. And before that, let me just name this combination of diode and a capacitor as a simple diode detector, which we have already discussed. So I told you that there are few extra components present in practical diode detector. So now after passing through the low pass filter, let us see how will the new waveform look like. So we have extracted the negative envelope, but that was with the high frequency ripples, and after passing through the low pass filter, these ripples will be removed and we will get much smoother waveform. So we will extract the negative envelope, which will be looking very much similar to the modulating signal, except the fact that it is in inverted form. All we have to do is provide an extra phase shift of 180 degrees so that it will become exactly similar to the modulating signal. Now that is not the only change. If you observe one more important thing, there is a DC shift present. There's a DC shift present in this signal because the envelope is shifted by some amount, some DC amount. So we have to somehow remove this DC component also. Now, because we have extracted the negative envelope, we have got negative DC component present. So if I can remove the DC component, this signal which we have, the modulating signal, it will be exactly present around the x-axis. So for that reason, we have got this C2 available, the capacitor C2, which is the blocking capacitor. It will block the DC signal and only allow the AC part of the modulating signal to go to the load side, which is in the form of R4. So if I draw my waveform at the output of C2, let's see how the waveform will look like. The waveform after C2 will be nothing but my modulating signal, which we had before C2 with some extra negative DC signal. So that DC is removed, and hence if you remove the DC, this waveform will shift upward and it will be present around the x-axis. Now let us try to understand why this extra circuitry of R2, R3 and capacitor C3 is provided. This R2 and R3 forms another path for the signal which was available at the output of C1. At the output of C1, the signal was my modulating signal along with negative DC signal. Now let us pass it through the structure formed by R3 and C3. R3 and C3, as you can see, R3 comes in the path of the signal and C3 is connected parallel to the input signal, and hence the structure of R3 and C3, very much similar to R1 and C1, will form another low pass filter. So low pass filter will only allow the low frequency to pass at the output side. Now what frequencies are present at the output of C1? At the output of C1 we have the modulating signal, which consists of audio frequencies, which will start immediately from 20 Hz. And apart from that, we have got a DC signal present. Now when I say it's a low pass filter, its cutoff frequency will be somewhere between DC signal frequency, which is 0, and minimum audio frequency, which is 20 Hz. So if the cutoff frequency is less than 20 Hz, that means this low pass filter will block the modulating signal as well, and output of the low pass filter will be only in the form of DC signal, and that too negative DC signal. So what have we obtained at the output of C3 is negative DC signal. Now we are saying that this negative DC signal is given to the circuitry which is called AGC. AGC stands for automatic gain control. We will discuss AGC separately, why we need AGC and what exactly AGC does. As of now, all you need to know that AGC will require a negative DC signal that is coming from the input signal, the signal which we have received. So now we answer that question we had formed in the beginning, that why the diode was placed in the lower branch and why we were planning to extract the negative envelope. The reason is we wanted the negative DC signal. To get the negative DC signal, we had extracted the negative envelope. And why do we need negative DC signal? It's because we use it in the circuit of automatic gain control. So that's our practical diode detector. To summarize everything, we have a simple diode detector in the form of diode and capacitor, and the output is the negative envelope with high frequency ripples. The high frequency ripples are removed using the low pass filter made up of R1 and C1. C2 will block the DC signal and give you pure AC modulating signal, which is also very smooth because of the use of low pass filter in the form of R1 and C1. R2 and R3 provide an extra path, an additional path for a signal at the output of C1, and R3, C3 they form a low pass filter with very low cutoff frequency. So from the DC signal and the modulating signal, the modulating frequencies will be blocked and the DC signal goes towards the AGC side.